Hello and welcome to today's webinar. My name is Jason Mercer and I will be your host today. Today's webinar is about the first class A1 effluent reuse permit in Montana, presented by my colleague Eric Blanksma. Eric will cover a range of topics associated with the process required to obtain a class A1 effluent reuse permit in Montana, the first of its kind. Eric is a professional engineer with Morrison-Maierle based out of our Helena, Montana office. He is a wastewater engineer with experience in planning, design, construction, and operations of wastewater plants, including MBR technologies. He holds a PE license in Montana, North Dakota, South Dakota, and Arizona. Before we begin, I want to mention just a couple routine housekeeping items. If anyone has a question during today's presentation, you can submit them through the question panel on your webinar interface, and we will answer as many as we can after the presentation. Today's webinar will also be recorded and posted to our website later this week, and we'll post today's PowerPoint slides if you would like to access those as well. If you are an engineer seeking PDH credits, this session may meet requirements for PDHs depending on your professional registration and/or certification requirements. If you're an operator seeking continuing education credits, this session is approved for 0.1 CECs. If you would like a certificate of participation to validate your attendance, please email Jenna Comstock, jcomstock@m-m.net to request one. Okay, without further ado, I'll pass the controls to Eric. And when you have them, Eric, take it away.
Okay, I think I've got everything passed over now, so I'll get started. I want to thank you for listening in on this presentation today. It's about the first class A1 effluent permit in Montana. It's located at Moonlight Basin in Big Sky, Montana. So a few of the topics I want to talk about today are effluent reuse, treatment selection, design and permitting, construction, and project challenges. This is a pretty broad overview of the project from start to finish, so we'll leave some time for questions at the end. This has been like I said, a 5-year project, and it's been very interesting to me, so I hope the things that we talk about today have some value in your projects. So just starting in on the Class A1 standard, and to give us a little background on why we ended up using it. The Circular DEQ2 Appendix B includes Class A1 standards, and that dates back to 2012. Prior to that, for landscape irrigation projects, were in the Chapter 120 of Circular DEQ2, and that had more limitations, specifically to agronomic uptake with respect to nitrogen. And with this Class A1 standard, one of the main reasons we looked at it was that we would be able to open up some opportunities with either landscape irrigation, groundwater discharge, or even looking forward to a surface water permit later. Some of the high points I'll point out are BOD and TSS need to be 10 milligrams per liter or less. The total coliform, we're looking at 2.2 CFU per 100 milliliters or less. Total nitrogen being 5 milligrams per liter or less. And then the filtration requirement keeping us at 2 NTU, which isn't listed here, but it's implied on there. One of the advantages too of Class A1 effluent is related to the groundwater discharge permitting that's typical, and if meeting the Class A1 standard, that is waived. So a few of the items that, or I guess ways that we can take care of our effluent on the A1 list here. There's quite a few, and I won't go through them all. I just wanted to put them up so that you can see that there's a lot of yeses under A1 in that column. And some of the ones we focused on were landscape irrigation, groundwater type discharges, and the stream flow augmentation, although that would require a surface water permitting effort. And then snowmaking is listed at the bottom there, and that's an ongoing discussion in Big Sky. So Moonlight Basin Resort it's been growing, and it originally started small, and so the first plant there was a trickling filter system, and then it had a nearby drain field. Later on, as growth occurred, they put in a traditional collection system and an oxidation ditch treatment plant, and that discharges to a storage pond and goes to forest irrigation. So the reason for the new plant was really to increase capacity as the development occurs, and also look for a better way to dispose of the effluent as opposed to the forest irrigation, which is at agronomic limits and requires a 200-foot setback. And another reason is Moonlight Basin is committed to using their water resources to the best of their abilities, and so this effluent is an important part of water use on the property. So we started out by looking at different treatment options and different disposal options, and in 2015 we finished up a preliminary engineering report. It included growth planning to handle their expanding development, and that would occur over a 20-year period. We looked at there's 3 drainage basins that traverse over the Moonlight Basin property and how to handle those. Each basin could either have a discharge or a outfall to its own plant, or all the basins could be piped together with lift stations and force mains to have a common single plant. So those options were looked at and considered and then scored. So as I mentioned, if we were able to bring all the wastewater together into one area, we could do a single MBR. Other options all included using the existing oxidation ditch for one of the existing service areas, and then putting in either oxidation ditches, SBRs, or MBRs for the other 2 treatment sites. So the treatment methods were determined by their ability to produce the effluent we were looking for. With oxidation ditches and SBRs, we still needed a tertiary filtration component. The MBR was able to combine that into that single treatment system. So the discharge options I mentioned, the Gulf irrigation, surface water discharge, and groundwater discharge, each have their own challenges. The Gulf or landscape irrigation is limited to what the golf course can handle as far as an annual flow, and that's approximately 20 million gallons a year. So that works for a period of time, but as growth occurs and the plants are expanded, that will eventually be one component of potentially many. On the surface water discharge, there are challenges with that as far as non-degradation with respect to changing the stream flow rate, nutrients, and then temperature. And there can be future study on that. We looked at that as more of a feasibility at this point, and trying to set it up for future consideration. And the groundwater discharge, we spent some time there exploring the property and looking for sites where there was soils that had infiltration that could handle the quantity of water we were looking at. We weren't able to find any where a large scale drain field or infiltration area could occur at that time. And again, that's something that's going to be, I'm sure, part of the future consideration in studies. And there is also just a groundwater aquifer recharge type option where water could be put down a well, and that's also takes more consideration, more study to determine the design approach for that. So in the near term, Gulf irrigation or landscape irrigation is the design basis for how we move forward. And Class A1 effluent is compatible with each option to some extent. It's just a matter of how we end up implementing that. On the selection, we chose the existing oxidation ditch and 2 new MBRs. This is just a ranking table that was part of our preliminary engineering report, and it just gives you some of the comparison parameters there that were used to make that decision. So moving on into the actual design, we chose to use a pre-selection approach because of the specifics that the MBR manufacturers have for each of their systems. We wanted to have a competitive selection to protect the client's interests so that they get the best product and the best value, and that also meets funding agency requirements, although this project is privately funded. So we worked with 3 manufacturers that we're familiar with and that have installations in the state of Montana, and we had them submit their information in an RFP and then conducted interviews as part of that process. And we had good client participation in the process. That was a really great thing. And in the end, 3 engineers reviewed and scored the proposals, and we did that independent of each other and then compiled that scoring at the end. So some of the information that was put out in the RFP that each manufacturer would have as their design parameters to keep things apples to apples and make sure that we had a common goal here. You can see that you have that 20-year period, although 2018 was an implementation number. The planning period was 2015 to 2035. So we started at a really low flow, 5,500 gallons per day, just enough to get started. And then in the 20-year design period, we'd be up to 104,700 on an annual average day. We used influent loading based on either sampling from the existing oxidation ditch, which they don't have a lot of data, but we used what we could find, and also used DEQ design values and chose the conservative of the two to make sure we covered those loadings. On the effluent design criteria, that just was intended to match up with Class A1 reuse. Let's see, next slide. So on the MBR requirements, here's just another table out of the RFP. And one of the things I'll point out is we chose to have 3 membrane trains. And the main reason for that was trying to decide how we could handle phasing and how we could handle those low flows. And we decided that it would be a better alternative to have 3 trains, 2 initially, and then the third could be added later. So we start out with 1 duty, 1 standby, and in the future we'll have 2 duty, 1 standby. All manufacturers needed to provide ultrafiltration in their membranes, and the rest of the parameters just kept us close so that each one could be compared. If they were going to deviate from this, we asked that they have a discussion with us, and we did work on some addendums through the project, although these did not change. So ultimately, GE, or now Suez, was selected for this project, and they provided a system, as I said, with the 3 trains, bioreactors, and membrane basins. They had a 4-stage process, so they have a pre-anoxic, aerobic, post-anoxic, and then an aerobic membrane basin, and that's due to the air scour that goes on in that basin. They had process chemicals, sodium hydroxide, micro C, and alum for pH adjustment, carbon source, and then if we needed to remove phosphorus for the alum. On the membrane chemical systems, fairly standard with sodium hypochlorite and citric acid that can be used periodically or on a larger scale, maintenance clean, or drain and clean over the course of operations. And they have a reinforced hollow fiber PVDF membrane. It's a ZWEED ZW500. So the process that they submitted is shown here. This is a BioWin output representation. So the first anoxic one is 8,300 gallons. The aerobic 1 and 2, they just split them up, but the total is 16,000 gallons. And anoxic 2 and 3 are also split, but total to be 8,300 gallons. We took and reviewed this BioWin output and created our own model to verify the outputs. And that was done for each manufacturer actually to verify. So the Moonlight Basin area, this is just an aerial view of showing the relation of the existing parts and the new parts. The existing oxidation ditch and effluent pond are over on the right hand side, and adjacent to that is where the forest irrigation has been occurring. So there's a force main coming up to that plant from down below at one of the lodge areas for the ski area, and that flow along with the central and northern service area will be reversed and sent to the new plant that this project is talking about. And then pond 3 over on the left-hand side is a 16 million gallon pond that currently is filled with water from Lone Creek on a surface water right and irrigated onto the golf course just to the north of that. And we were able to connect onto a pipeline and send water up to that pond 3 area, and that will become the discharge point for golf course irrigation. As I mentioned before, there's three drainage basins over Moonlight's development area. The existing oxidation ditch covers existing developments that are off screen to the south, and the new plant, like I mentioned, would be the central and northern, and then a third potential plant would be further west in the smaller, sparser development area. So just a couple things to talk about on the plant site plan. Although the building is set up to be seen, it had a lot of architectural items on it to help with the view shed. But one of the improvements to the site was this berm on the right-hand side of the plant, and that just keeps the plant from being a central focus of the view shed looking down. The plant site was already flattened as a previous project, and we ended up putting 2 buildings on, one for treatment, one for solids, and all the processes are inside or under roofs, and this site plan allows space for snow removal and adequate access. So the plant process flow diagram shown here gives you an idea of some of the processes that are going on. So Effluent enters the plant, it goes through fine screens, through vortex grit, into an Effluent pump station, and from there it's lifted up into the bioreactor splitter box. It overflows by adjustable gates into the 3 bioreactors, and then into the membrane basins. Filtrate has to be pumped out of the membrane basins through the UV reactor and into the effluent basins, which supply NPW, back pulse, and effluent discharge. On the return sludge streams, those are all pumped in the bioreactor, and the waste stream is pumped to the digesters in the solids building. Solids can be pumped from the digesters into the dewatering press or to load a truck. You can see here we have land application either by liquid or by cake. So another way of looking at this is the hydraulic profile. And again, we start by gravity flow into the plant. We drop down into that influent pump station, lifts it back up, and it's able to gravity down to the membrane basin and then pumping from there. So the plant layout, this is the main building. We, like I mentioned, kept the processes under a roof and heated in this case, just due to the climate and the snow load that there would be, and icing. So on the upper right, we have our headworks, which is separate from the rest of the building. It's ventilated at 12 air changes per hour, and it's a class 1 div 2 space. Then the rest of the plant is unclassified. The chemical feed areas are separate off to the bottom right, and mostly each chemical has its own area. There are a couple chemicals that are allowed to be together. There's not an incompatibility issue there. We provided an office, laboratory, restroom, and laundry area for the operators on the upper left. And then there's a dedicated electrical room. So underneath that level, there is a lower level, and this is a help with providing flooded suction to our pumping systems. And so on the right-hand side, you can see the 3 Effluent pumps. They're able to be in a dry pit configuration, taking water from the Effluent pump station wet well. On the membrane area, we're able to pump mixed liquor out of the membrane basins in a flooded suction configuration. And then on the NPW and Effluent pump skids, we're able to also pull those out with flooded suction. So the lower level utilized the footprint the best way we could, staying under that roof and being protected in a heated and separate space. This is the solids building. So we have 4 20 by 20 dimension aerobic digesters with fine bubble diffusers. Then we have a piping gallery, which was also designed to allow operations of the valves, either moving water in or out of the digesters without having freezing issues or searching for a valve under a snowdrift or those types of things. And then we have a positive displacement pump down in that gallery in a flooded suction configuration that can feed our screw press. And then on the left-hand side, our digester blowers feed air to the basins and the diffusers. So permitting of the project, we worked through plans and specs and finished with a submittal to DEQ in August of 2016. And while it was under review, we were asked about information on the storage pond 3 and the golf course irrigation. And so we spent some time going through that, doing some further study, and having a geotechnical report put together for the pond, and then also looking at the golf course and how down to where the sprinkler heads are aimed, and making sure that we don't discharge water to a surface water drainage. And so on January 23rd, 2017, we had our DEQ approval for the project. So this photo here was just showing doing a leakage test on that pond 3 liner. So as part of the permit, here are the monitoring requirements. Since it's not a groundwater discharge permit or a surface water discharge permit, these were written into the actual approval for the plant. And you can see that in year 1, there's a lot more sampling, and then it tapers off at 4 and beyond. So construction of the project, after a pause of approximately a year, just due to development needs and the client programming this project, we started into the construction with bids due on January 2018, and Dick Anderson Construction was the low bidder. And over the course of the next few months until May, we worked through budget issues and just some value engineering and just some of those things that they, when they looked at the site and everything and how things were going to go together, they had some ideas, and that gave us enough time to begin work in May 2018 after ski season was finished and when weather permitted. So the project was completed in November 2019, and the final amount was 8.63 million. And the photo here just shows about 1 or 2 days into it, just clearing the site and starting to dig for the large water holding basins. So one of the nice things about this site is the hillside behind it provides a really good place to take photos, and so we were able to pick up a good timeline on the project, and you can see in the first couple months here, July and August, as structures started going up, they focused on the solids building, as it was a little bit simpler construction and not quite as deep, and then they moved to the bioreactors, which are 18.5 feet depth, water depth, and started building those up. One of the design aspects that we focused on was providing a base slab that then we could build up off of and try to limit sequencing as best we could, because each pour requires curing and then concrete breaks to move to the next level or a backfill. So keeping sequencing down was an important part of that design. So moving into the next few months, you can see that water testing occurred in the digesters, and we started to see the treatment building coming up out of the ground. And on the September photo, you can see the steel structure that forms the floor between the ground level and the lower level, and that structure allows for vehicles to be driven through that bay on the north end of the bioreactors. And then in October, you can see the building going up over the solids area, and then in the main building, we can see some of the structure work in the headworks. You can see the screening channels taking shape on the lower right, and then the gravity sewer was being installed. So one of the biggest challenges that we came across on the construction was just trying to get everything dried in before winter so that they could continue work inside and not be shut down for the winter. And initially it was thought that pre-engineered steel buildings would speed it up, but in this case we had a supplier issue with the buildings not coming in as fast as the contractor had originally wanted. And so we're into November here, and they're still fighting with the elements, trying to get the building put together. Luckily, the solids building was in better shape, but this was the main building. So by January, finally, we're able to get the shell and the roof around the building, and we're able to work inside. One thing you'll notice on the left-hand side photo is that we didn't enclose the area over the digesters, but we did put a roof over it to prevent them from filling up with snow. But we wanted to make sure that there was adequate ventilation and while the digesters are running, as opposed to closing those in. So fast forwarding, you can see this is membrane installation, and just point out a few things on the right hand photo. the reason I fast forward is because all the photos of putting together piping and putting in pumps, there's tools laying around and things weren't as clean. But getting to this point, you can see that all the systems in the building, there's HVAC ducts, there's electrical cable trays and conduits, there's piping feeding all the systems. And then we finally get to this point where we're ready to install the membranes. Above the membrane cassette, you can see hoists that are over each train. And those allow installation as well as maintenance over the life of the facility. And then we have solid grading over each membrane basin to protect from anything falling in. One of the design parameters they could point out is that hoist and that membrane cassette excuse me, determine how tall the building is, and that is the lowest point where the roof line comes down and where that membrane can still clear over the concrete basin. So that set the building sidewall at 20 feet. On the left-hand side picture, you can just see how the frames for the manufacturer provided frames mount into the concrete basin, and then those cassettes slide right down in. So at the end of September, equipment was started up and they were able to start seeding the plant. And so, like I mentioned before, the volume of one train of the basins is approximately 32,000 gallons. And so that was brought up from the Big Sky County Water and Sewer District, and they have an SPR treatment plant approximately 8 miles away in the Meadow Village. So this is the plant when it was completed, and you can see that the building has a lot of those architectural elements I mentioned to fit in with the area, and most people who have seen it don't attribute it to being a wastewater plant at all. So we'll go through a few photos of some of the systems in the plant. So we have the fine screens on the left-hand side there. We have two millimeter fine screening systems. And then on the right-hand side, that's the dry pit area with the 3 influent pumps. We have the ability to meter flow out of that influent pump station up into the bioreactors. And then we allowed a stub for a future equalization basin pipe if needed. And on the digesters, there's actually the ability to feed influent into those or mixed liquor if we ever need to. With the size and the volume there is, we have some ability to use those as equalization. So that's an important part of the plant as far as allowing for flexibility if there's maintenance needs. On the main floor here, we can see the finished bioreactors in UV, and up on top of the bioreactors we have grading where it's accessible to walk up and look at the instruments, and we can access the mixers that are rail mounted, or there's rail mounted pumps that are part of the recycle stream from the aerobic back to the first anoxic basin. In the lower level, we have our blower area, and part of the consideration of having the blowers in the lower level was just noise and keeping that away from the operator admin area upstairs, and the blowers actually are very quiet, but that was part of the reason to have those in this lower level. And similarly with the pumps on the right hand side, we have filtrate pumps and mixed liquor return pumps for the membrane systems located in that lower level. All very accessible and separate from the upper level, where they have some ability to store equipment or move vehicles through. In the digester area, just showing the diffusers in one of the digesters, and then we have a nice access walkway that we can get to all 4 digesters and the telescoping valves and the airflow monitors or any other isolation valves. And that's all under the roof. So like I mentioned before, there's not going to be a lot of snow on this walkway, which is nice. So I'll just go through a few of the challenges and how we approach those on this project. You know, starting out looking at how to handle this treatment and disposal, it seems like a daunting task, but just had to start and compile this preliminary engineering report to study and recommend the solution that we came up with. And only after you start putting together all that information that starts becoming more clear what needs to happen. And we had a really good client, they wanted to participate and be a part of that, and that's always helpful because ultimately it's their facility that they're gonna run, and it's gonna meet their needs in the future. With first of kind permitting, just doing upfront research and homework to figure out if what you're proposing is gonna be approvable, and looking at maybe what people are doing in surrounding states or other areas, and then communicating with regulators up front. And we had worked through some of those communications and meetings definitely up front, and it felt like Class A1 effluent had some excitement, and people were very supportive. With existing infrastructure, just planning ahead, because if you need to permit existing infrastructure, you need to find out if there's actually records available that can help determine if it's approvable. And then if there are other inspections or testing, those need to be scheduled and other reports. And in our case, with the effluent pond that we needed to permit, it was designed with effluent storage in mind originally, which was helpful, but it still needed inspections and testing that took us a little bit of time to take care of while we were doing the permitting. On construction, in our case, we had a challenging site being in Big Sky and just not being as close to materials and labor, and then also dealing with the short construction season. And so just taking that into the account in designs and trying to think ahead on what's going to work best for the site. And then on starting up a plant is not an easy task, especially in our case where they don't really have flows to start out with. And I would say that providing some operational support is an important thing, and it's an important discussion to have with owners and engineers and contractors on how to go about that first few months or even a year of initial operation to make things successful and to make adjustments as needed. So with that, at the end of the presentation, and we'd be happy to talk over any questions you might have. So I don't know if anybody is
Yeah, Eric.
anything, or I'll turn it over to Jason and he can take a look.
Yeah, we've got a few questions coming in here. Just a reminder that if you do have a question, please submit that through the webinar control panel so that we can pose those to Eric. Maybe the first question that I'd ask is, what lessons learned would you offer in navigating the permitting process for this type of permit? And I guess the question is, was there any data you wish you would have collected beforehand or had available to help through that process?
Well, I think I mentioned that with their existing irrigation in the forest, they didn't collect a lot of data on the influent of their plant. They collect data on the effluent. And so the more influent data that operators can collect over a time period and compile, the better that they'll be set up for studying and finding a solution as they move into an expansion or a new plant that they need to look at. So I would just encourage operators to keep that data, even though I know it's a cost for sampling, but it's hard to go back years and wish you had it. So
yeah, the more data you have, the more you can do with it. Second question that's come in is how well is the plant meeting the discharge limits?
So right now, we're still under our initial startup, and so we were hoping for a better flow coming in this ski season, but it got cut short. And so right now they're working on providing a way to bring some influent down from their existing plant. And we need a minimum of 5,500 gallons per day to really feed the plant and to get to where Suez feels comfortable with things. And so right now we're able to nitrify, but our denitrification hasn't fully developed yet. We do get really good filtration, obviously, and that's somewhat of the easier part. But yeah, total coliform is non-detect, and turbidities are in the 0.2 range. Actually, yeah, 0.2, and then so it's a work in progress as far as that goes. If we can get flow to it, then we'll be able to develop the biology better.
Another question for you, Eric. You mentioned that the owner was very engaged. Were they at all concerned about operating a membrane plant as you were evaluating options?
Yeah, they were, but they were also, I think, excited about the opportunity and what the technology can do. And so just I think there's probably a healthy fear of it, but there's also the excitement that was overtaking that. And I think that the operators are very proud of their plant at this point and excited for the future.
Let's see, another question's come in kind of related to the membrane evaluation. And so when comparing the different membranes from the manufacturers, did you find them to be pretty similar, or are there pretty drastic differences between the membranes from the different manufacturers and their performance?
Performance-wise, I would say they were ultrafiltration, which was our requirement. So the performance of what will pass through is fairly similar. They each have their own air scour system. So there was some energy calculations that go into that. we had 2 hollow fiber membrane submittals and 1 flat plate. So again, those are just, they have different scour requirements and different approaches, but in general, they're similar, I guess, but they're all different enough that that's why we wanted to choose one up front.
Kind of a follow-up is, are they, similarly priced between those different types of membrane styles, or was there quite a difference?
So yeah, there was a range for sure. They weren't all very, very close on capital costs, but then we had to look at O&M costs and membrane replacement costs. So those are a few of the items. The big item, honestly, on this project was we gave them the ability to choose what process they wanted to put forward for the biology. And so that was a, tiebreaker beyond just what they cost. But they were, they're generally in a similar range just on capital cost.
Given the location of this project up in Big Sky, was there any kind of public process for the siting of the plant or the building that went around the plant?
Yeah, there is. There's an architectural review board for that, and the owner actually took care of that part of it, and we interfaced back and forth as needed to make adjustments. But the berm was one of the items that they wanted incorporated into the project.
See, maybe the kind of the final question that I have, or I'm seeing, is was there, with the aerobic digesters being outside but yet having a roof over top of them, any issues with snow blowing in around the corners, or performance issues with those?
Yeah, so far they haven't really produced solids, but initially they did have water. They were taking effluent and circulating it through and reusing it in the plant, and so the big issue is just keeping enough water in there, either draining it or putting water high enough so that it doesn't catch on the diffusers. And at some point in the future, when they have more solids and more circulation through there, then I think it'll work a little bit more smoothly. But right now, they just need to make sure that they don't freeze those diffusers.
All right. Thanks, Eric, for the presentation. That was very good and informative. Just switching screens here. So with that, just a reminder, we will post the PowerPoint slides and recording of today's presentation on our website at m-m.net. And hopefully you're able to join us on Thursday, May 21st at 12 p.m. for our next webinar on dialing in a membrane bioreactor for nutrient removal. That presentation will be put on by Rika Lashley. Finally, we'd love to hear from you. Please stay in touch with us on social media through Facebook, Twitter, Instagram, and LinkedIn. Really appreciate your time today. Thanks for tuning in. We hope you can join us next time. Until then, be well and be safe.